In this video, we're going to start Chapter 5 of the chemistry textbook. Chapter 5 is about gases. Okay, under certain conditions of pressure and temperature, most substances can exist in any of one of the three states of matter: solid, liquid, or gas. Water, for example, can be solid ice, liquid water, steam, or water vapor. The physical properties of a substance often depend on its state. Yeah, so it's important to remember that, in general, any substance, no matter what it is able to exist in a solid, liquid, or gas state. Now, it's not the case that what we refer to as more normal conditions, so room temperature and atmospheric pressure, all substances are able to exist in the solid, liquid, or gas state. But like it says, at some combination of pressure and temperature, even if it's what we would refer to as a more extreme condition of temperature and or pressure, you can think about how in general any substance can exist in the solid, liquid, or gas state. Okay, so gases, the subject of this chapter, are simpler than liquids and solids in many ways. Molecular motion in gases is totally random, and the forces of attraction between gas molecules are so small that each molecule moves freely and essentially independently of other molecules. Subjected to changes in temperature and pressure, it is easier to predict the behavior of gases. The laws that govern this behavior have played an important role in the development of the atomic theory of matter and the kinetic molecular theory of gases. So, yes, one thing you want to remember about gases, or a substance in the gas state, is that in general, gases are simpler than liquids or solids. Simpler from the perspective of it's easier to analyze gases or describe gas properties. It's easier to predict the behavior of gases. In comparison to solids, for example, solids get very complex. You have polymers, metals, etc. Metals contain crystals, grain boundaries, dislocations, vacancies. There's all kinds of different crystal structures. Now, but if you're somewhat familiar with gases already, you might be thinking that gases are only simpler when dealing with an ideal gas. We're going to talk about ideal gases versus real gases in this chapter, but no, that's not what the textbook is saying here. Even for something that we would call a vapor instead of a gas, like water vapor, for example, it's called a vapor because it's a substance in the gaseous phase that's normally a liquid or solid at room temperature, while something that's called a gas is something that's naturally in the gas state at room temperature. But the statement the textbook is making here is in reference to vapors as well. This statement is in reference to any gas whatsoever, even like a metal that's vaporized. Anything that is in the gas state is going to be relatively much simpler to analyze than a substance in the liquid or solid state. Okay, so we live at the bottom of an ocean of air whose composition by volume is roughly 78% nitrogen into 21% O2, oxygen, and 1% other gases, including CO2. Today, the chemistry of this vital mixture of gases has become a source of great interest because of the detrimental effects of environmental pollution. The chemistry of the atmosphere and polluting gases is discussed in Chapter 20. Here we will focus generally on the behavior of substances that exist as gases under normal atmospheric conditions, which are defined as 25 degrees Celsius and 1 atmosphere pressure. The figure below, the periodic table below, shows the elements that are gases under normal atmospheric conditions. Note that hydrogen, nitrogen, oxygen, fluorine, and chlorine exist as gaseous diatomic molecules, right? So like H2, N2, O2, etc. An allotrope of oxygen, ozone, O3, is also a gas at room temperature. All the elements in group 8A, the noble gases, are monoatomic gases. So they're not in a molecular form, just the neutral atom. You zoom in on the gas and you just see these individual neutral helium atoms flying around everywhere, neon atoms flying around everywhere. As opposed with these elemental forms of oxygen, nitrogen, hydrogen, you would see these O2 molecules flying around everywhere, F2 molecules flying around everywhere. So yes, something you want to keep in mind when looking at the periodic table is that elemental forms of a given element are going to exist as a solid, liquid, or gas at what the textbook states here are normal atmospheric conditions, being 25 degrees Celsius in 1 atmosphere. 25 degrees Celsius, that's 77 Fahrenheit, so room temperature, or actually a little bit above room temperature. And then 1 atmosphere is the atmospheric pressure at sea level, but we'll talk more specifically about the pressure unit of atmospheres, ATM, later in the video. So these normal atmospheric conditions are what are referenced when discussing general properties of elements in the periodic table, or any substance, really. It doesn't have to be a pure elemental form. So when making general statements about properties of a substance, it's implied that these statements are in reference to that substance being in a room temperature environment with a pressure of 1 ATM, 1 atmosphere. Because, like we talked about, substances are going to have different properties depending on the environmental conditions, right? In general, any substance is able to exist in the solid, liquid, or gas state depending on the temperature and pressure of the environment it's in. So you really can't talk about the properties of elements or substances without also having an implication for the conditions of the environment that substance is in. Okay, now, but don't confuse this with standard temperature and pressure. You'll hear the phrase standard temperature and pressure, or STP, thrown around a lot. Notice the textbook didn't say anything here about like a standard temperature or pressure, or STP. It just used the term normal, and normal wasn't even bolded or italicized or anything. The term normal would be referring to room temperature, and a pressure of 1 atmosphere is a reference for atmospheric pressure at sea level, which we're going to talk more about later, the atmosphere. But even then, what's room temperature, right? To me, room temperature is 72 degrees Fahrenheit, but 25 degrees Celsius is 77 degrees Fahrenheit. So we'll talk more about standard references for the environment of some system later. But just here, the idea is, all you want to remember is that when discussing the general properties of elements in the periodic table or any substance, even non-elemental forms, unless stated otherwise, it's implied that the discussion is in reference to these substances being in a room temperature environment at a pressure of 1 atmosphere, 1 ATM. So, okay, at normal atmospheric conditions, most metals are going to be solid. However, there are some exceptions. Mercury, for example, is a liquid at normal conditions. Cesium and rubidium are solids at normal conditions, but their melting points are just above room temperature. For nonmetals, bromine is a liquid at normal conditions. Carbon, phosphorus, and sulfur are solid. Iodine is a solid, but all of the elements that the textbook highlights in blue are gases at normal conditions. And as you can see, these are all non-metals. Now, also remember that when saying that these elements are gases, really when making any reference to the state of an element in the periodic table, we're referring to elemental forms, stable elemental forms of the element at normal conditions. And so like it said, hydrogen, nitrogen, oxygen, fluorine, chlorine are most commonly going to be diatomic molecules. The noble gases are unique, however, in that they're just single monoatomic neutral atoms. In the solid, liquid, or gas state for a noble gas element, they're called noble gases because they're gases at standard conditions and are very hard to condense. You need very low temperatures and high pressures to condense them, but whatever the state for a noble gas, if you could zoom in on it at the atomic level, you would see individual neutral elements of this group 8. Okay, ionic compounds do not exist as gases at 25 degrees Celsius and 1 atmosphere because cations and anions in an ionic solid are held together by very strong electrostatic forces. That is, forces between positive and negative charges. To overcome these attractions, we must apply a large amount of energy, which in practice means strongly heating the solid. Under normal conditions, all we can do is melt the solid. For example, NaCl melts at the rather high temperature of 801 degrees Celsius. In order to boil it, we would have to raise the temperature to well above 1,000 degrees Celsius. So, yes, we're going to learn in chemistry how what's responsible for causing a substance to exist in the solid, liquid, or gas state is forces that are at play between the individual particles. Individual particles meaning, so if you imagine any substance, no matter what it is, in the gas state, then what are the forces at play trying to pull and keep the individual gas particles together? The smaller these forces, then the more favorable it is for that substance to be in the gas phase. The larger these forces, then the more favorable is a liquid or solid state. Well, of all substances that exist, forces between particles don't get any more significant than with ionic compounds. So like sodium chloride, for example, in the gas state, what you would have is individual Na plus and Cl minus ions flying around everywhere. So the force between particles trying to pull and hold these particles together are ionic forces, right? Compare this to another substance like water, in which the forces are forces between molecules that come from the polarity of the molecules. So that's why the textbook is saying how any ionic compound, no matter what it is going to exist as a solid at standard conditions. So not even a liquid. The forces between particles are so strong that you get a rigid, solid connection between particles. And so to overcome these forces between particles, you need a high amount of energy. An ionic compound in a liquid or gas form is going to need to be in a high temperature environment and low pressure as well. Okay, the behavior of molecular compounds is more varied. Some, for example, carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, and methane are gases, but the majority of molecular compounds are liquids or solids at room temperature. However, on heating, they are converted to gases much more easily than ionic compounds. Okay, so they're talking about molecular compounds, so not elemental forms, but molecules composed of two or more different types of elements. And it says the majority of molecular compounds are liquids or solids at room temperature, but some are gases, carbon dioxide and methane, for example. But even the molecular compounds that aren't gases at standard conditions are much easier to convert to gases than ionic compounds. Okay, so here in the table, they list some different elemental forms and compounds of substances that exist as gases at standard conditions. So here's the hydrogen, H2, O2, F2, the noble gases, and then compounds. You have hydrogen fluoride, hydrogen bromide, carbon dioxide, hydrogen iodide. There's hydrogen chloride, nitrous oxide, etc. Okay, there is no simple rule to help us determine whether a certain molecular compound is a gas under normal atmospheric conditions. To make such a determination, we need to understand the nature and magnitude of the attractive forces among the molecules, called intermolecular forces. In general, the stronger these attractions, the less likely a compound can exist as a gas at ordinary temperatures. So we're going to learn more about forces between molecules or individual particles of a substance and how they relate to the state of a substance, whether or not it's in the solid, liquid, or gas state, in Chapter 11. Okay, of the gases listed in the above table, only O2 is essential for our survival. Hydrogen sulfide and hydrogen cyanide are deadly poisons. Several others, such as carbon monoxide, nitrogen dioxide, ozone, O3, and sulfur dioxide are somewhat less toxic. The gases helium, neon, and argon are chemically inert. That is, they do not react with any other substance. Most gases are colorless. Exceptions are F2, Cl2, and NO2. The dark brown color of NO2 is sometimes visible in polluted air. So yeah, there's NO2, gas. All gases have the following physical characteristics. So gases assume the volume and shape of their container. Gases are the most compressible of the states of matter. Gases will mix evenly and completely when confined to the same container. And gases have much lower densities than liquids and solids. And you can think about this third property is one of the characteristics of gases that make them so simple and easy to analyze. Because no matter what, they're going to mix evenly and uniformly. As opposed to, like a metal, the way it will crystallize, it can crystallize in all kinds of different ways. Okay, gases exert pressure on any surface with which they come in contact because gas molecules are constantly in motion. We humans have adapted so well physiologically to the pressure of the air around us that we are usually unaware of it, perhaps as fish are not conscious of the water's pressure on them. It is easy to demonstrate atmospheric pressure. One everyday example is the ability to drink a liquid through a straw. Sucking air out of the straw reduces the pressure inside the straw. The greater atmospheric pressure on the liquid pushes it up into the straw to replace the air that has been sucked out. Yeah, so gases and liquids are considered fluids. And we describe the property of fluids or gases or liquids related to force in terms of the pressure of the gas or liquid. So like it mentioned here, gas pressure comes from the particles of a gas colliding with the surface that they're in contact with. Because any substance, no matter what phase it's in, on an atomic level, a molecular level, the temperature of the substance is directly related to the degree and intensity of which the molecules or particles or atoms are moving. In the case of a solid, that's going to be movement in relation to vibrations. And then in a liquid, in a gas, you'll have vibrations as well as linear motion. We're going to learn more about this relation of temperature to the motion of a gas later in this chapter. But what they're talking about here is it's this motion of the gas particles and their collisions with the surfaces they're in contact with. It's the net collisions of these moles of particles with the walls of a container, the net force caused by these collisions, that is what we describe as the gas pressure. Okay, and so the only way to describe the force property associated with fluids, and this is what makes fluids so simple, there's only one way to describe this force property of a gas or liquid, is with pressure. So here in this section, it goes through a whole unit derivation of pressure in terms of, so like a force is a mass times an acceleration, right? That's what Isaac Newton discovered. So then you can go through a whole analysis where you have mass times acceleration, so that's like kilograms, and then times meters per second squared, and then that's divided by the force is divided by an area, so square meters. Okay, but we're not going to go through the whole unit derivation. But what it comes down to is in SI units, the unit of pressure is the Pascal, and this is just 1 Pascal is 1 Newton per square meter. So a Newton is a unit of force, right? And a square meter is a unit of area. But then there's also like PSI, that's pounds per square inch. Pressure is a force divided by an area. Okay, and so now why is pressure really the only way you can describe the force property of a fluid, of a liquid or a gas? Well, the idea is if a fluid, so a gas or a liquid, is in contact with any surface, no matter what the orientation of the surface, it could be on top of a surface, you got this liquid or gas on top of a surface, or it could be like the surface is, the fluid is underneath it, so it's in contact from below, whatever, or from the side. Here's the fluid, and it's in contact like this. It doesn't matter. If a gas or liquid is in contact with any surface, but that gas or liquid has a certain pressure, let's say given in pascals or PSI, but you can use any unit of pressure you want, any force divided by area you want, then the idea is let's come to this orientation here. Let's say we were laying down right here and looking up. So now we're looking up at this surface here from underneath, okay? The idea is, let's say we're thinking about in PSI. If you would highlight a square inch, it could be actual square, so 1 by 1, or you could do like a square inch like this, whatever. As long as the area is 1 square inch, then the force exerted by the liquid or the gas on that area, the net force, like the total average force, is equal to whatever the pressure is. So if the pressure was 50 psi, then on each of these 1 square inch areas, the average force would be 50 pounds. And then, but like if you were looking at an area of 2 square inches, and the pressure of the liquid or gas was 50 psi, then the total average force on this entire area would be 100 pounds. Okay, so that's how pressure works, the pressure of a liquid or gas. Okay, now the atoms and molecules of the gases in the atmosphere, like those of all other matter, are subject to Earth's gravitational pull. As a consequence, the atmosphere is much denser near the surface of Earth than at high altitudes. The air outside the pressurized cabin of an airplane at 9 kilometers is too thin to breathe. In fact, the density of air decreases very rapidly with increasing distance from Earth. Measurements show that about 50% of the atmosphere lies within 6.4 kilometers of Earth's surface, 90% within 16 kilometers, and 99% within 32 kilometers. Not surprisingly, the denser the air is, the greater the pressure it exerts. The force experienced by any area exposed to Earth's atmosphere is equal to the weight of the column of air above it. Atmospheric pressure is the pressure exerted by Earth's atmosphere. The actual value of atmospheric pressure depends on location, temperature, and weather conditions. Yeah, okay, so that's what atmospheric pressure is. It's a gas pressure created by the entire weight of air on top of us. And it's similar to how in the ocean, the water pressure is created by the water on top of you. But it's kind of tricky when you first learn about pressure from a fluid pressure from a liquid or a gas, in that the degree of pressure is only based on how much fluid is vertically above a certain point. If you think about the pressure at a certain depth in the ocean, at the ocean floor, whatever, then that pressure is only based on the vertical height of water above you. So like, okay, in the ocean, if you're in a submarine, you're at a certain depth, it's not that the entire weight of the ocean is on top of you, like all of the water in the ocean is weighing down on you. No, not at all. Like for those submarines that dive very deep, let's say, for example, you had a really strong metallic straw. So just like a regular straw, but it's this really long straw that's made out of metal to hold the water pressure. And this straw was the same length as the depth a really deep submarine dives from the ocean surface. Okay, so you've got this straw at your house, in your yard. It's this really, really long straw, like a 12,000 foot long straw. Okay, now let's say that it's filled with ocean water to the top. And then let's say, so this is in your yard, and you've got here, it curves like this. So you can, and there's like a valve here. There's a valve here to where all the water is held in the straw, but when you want to open the valve, it's all going to come shooting out here up into the air. All right, so this is like 12,000 feet. I want to say the Titanic is about 12,000 feet deep. Okay, well, what the water pressure at the depth of the Titanic means is that, like, it has the exact same meaning as this straw in your yard. As far as the pressure at the valve, the water pressure is the exact same as it would be if you're in a submarine at the depth of the Titanic. And physically, what this means is that if you were to open this valve, the moment you open this valve, that water pressure is going to result in this water shooting out with a like extreme velocity and extreme intensity. Right? It's going to be extreme pressure. This water is going to shoot out a huge distance at a huge velocity. And it would be the same exact idea if you could kind of like have a straw in the ocean, or no, if there was a hole opened up in the submarine, the water would come shooting into the submarine with this exact same velocity. Okay, so but then what's the difference then? What's the difference between like the water pressure here with this straw and then the water pressure at the depth of the Titanic? The difference is that the water in the straw is going to get consumed very quickly. This pressure is not going to last long at all. You're not going to be able to maintain this stream, this high velocity of water from the straw for very long because you don't have a big source of water to pull from. As opposed to with the ocean, this velocity of water, this pressure, once you open the valve, would last significantly longer, right? It would take the level of water, the height of the water, which is what the pressure is based on. If you had all of the ocean water as your source, this would just creep down extremely slow, very slow. It would just, you have this constant stream forever. And the pressure would decrease just slowly, 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 as opposed to with the straw, this level would drop fast. And all of a sudden you would have no pressure quickly. But initially, right at the beginning, the pressure is the same. The fierceness and intensity of the water coming out right at the moment you open the valve would be the same as if a crack opened up in a submarine at the depth of the Titanic, at least at that initial instant. Okay, and so like it says, in regards to atmospheric pressure, this chapter is about gases. We interpret atmospheric pressure as it's the weight of the column of air above it. So like if you're at ground level, what is the weight of the column of air above you? And they're using this analogy of a column of air because they're trying to give you that sense of it's strictly about the height of the fluid, the air on top of you. There's nothing to do with the volume, that the air pressure has nothing to do with the large volume of air on top of you. It's just about the height. That's it. And so like if this area here was 1 square inch and you were so atmospheric pressure is at sea level is 14.7 psi. So the idea then is if you were at sea level and let's say this square was 1 square inch, then this entire column going from sea level to the into the atmosphere would contain 14.7 pounds of air. That's the idea. Now, this might be kind of confusing to you in the sense that how is a gas weighing down on us? It's intuitive to think about a solid sitting on top of you, like weighing down on you. Even a liquid like water pressure in the ocean makes sense. Water can be weighing down on you, but not so much a gas. How does the weight of a gas work? Well, the way I like to think about it is if you really think about a solid or liquid substance on the atomic level, it's kind of a head scratcher how pressure would work with those substances as well. Like as we know, atoms are mostly empty space anyway. But still, it's kind of tricky to think about the idea of the weight of a gas on top of you as opposed to the idea of the weight of a solid or liquid on top of you. I think is more intuitive. Okay. So, does atmospheric pressure act only downward, as you might infer from its definition? Imagine what would happen then if you were to hold a piece of paper tight with both hands above your head. You might expect the paper to bend due to the pressure of air acting on it. But this does not happen. The reason is that air, like water, is a fluid. The pressure exerted on an object in a fluid comes from all directions, downward and upward, as well as from the left and from the right. At the molecular level, air pressure results from collisions between the air molecules and any surface with which they come in contact. The magnitude of pressure depends on how often and how strongly the molecules impact the surface. It turns out that there are just as many molecules hitting the paper from the top as there are from underneath, so the paper stays flat. Exactly. So we think about a gas or a liquid as a body. You have a gas body or a liquid body. And the body is just all of the gas or liquid enclosed by an imaginary surface. So for any gas or liquid body, the body is you enclose the entirety of that gas or liquid with this imaginary surface. right? So you would consider all of the gas inside this boundary as a gas body. Now, thinking about a gas body, usually this boundary surface that encloses the entire gas body is going to correspond to whatever container the gas is in. All points on the entire boundary surface are going to be meshed with the surface of the container that contains the gas body, right? Because like it said here, a property of gases is that they assume the volume and shape of their containers. However, with the atmosphere, this is obviously a little bit different. The Earth's surface is like a container containing the atmosphere on one side, so the Earth's surface can push back on the atmospheric gas molecules and resist their motion, right? But on the other side is empty space or a vacuum. There's nothing pushing back on Earth's atmospheric gas particles at the edge of space. Now, but as far as the imaginary boundary enclosing the gas body of Earth's atmosphere, again, one boundary would line up with Earth's surface, but then another part of the boundary would line up with the edge of the atmosphere at the edge of space, at the point where you go from having some, even if it's not many atmospheric gas molecules, to pure vacuum. So like Earth's atmosphere, just like any gas or liquid body in the universe, is enclosed by an imaginary boundary. It's just that this boundary for Earth's atmosphere at the edge of space would not be a boundary that's pushing back in any way on the gas particles, which is not what we as humans typically are accustomed to with a gas body. The gas bodies that we're typically familiar with are fully enclosed in 3 dimensions on all sides in a container, like a pressure vessel, for example. And in these cases, the general idea is that there's one uniform pressure of the entire gas at a time. If the pressure in a pressure vessel that contains a gas is, let's say, 100 psi, like this air compressor, for example, it's like a home air compressor you could buy at Lowe's or Home Depot. On top is the compressor, and on the bottom is the container that holds the compressed air. So this is like a pressure vessel. Well, when we think about this as like for the entire body of compressed air in the tank, the gas body surface boundaries is in that case is the walls of the container. Well, if the pressure gauge on the compressor says 100 psi, then what that means is that the way we interpret that is at all points in 3D space throughout the entire compressed air gas body, the pressure is 100 psi. Therefore, what this means is that any surface this air is in contact with, no matter what the orientation, upside down, to the side, so, in a general pressure vessel, the air or whatever the gas is contacting the surface from all orientations. Here it's upside down at the top. Here it would be pushing down. Here it's pushing to the side. And the idea is that for any surface the air is in contact with, if you looked at a square inch of that surface, then on average across that area, the air is pushing with a force of 100 pounds. 100 pounds per square inch. If you did 2 square inches, it would be 200 pounds. If you did a half of a square inch, it would be 50 pounds. And the direction of this force is always, in every case, normal or perpendicular to the surface. There's no component of the force that's parallel to the surface, like a friction force would be. And the reason is because fluids, gases or liquids, can't support shear forces. So you describe the force nature of a gas or a liquid with pressure, and fluid pressure is only going to act normal or perpendicular to the surface that it's in contact with. Okay, but now with the atmosphere, it's a little bit different. It's not what we're accustomed to seeing with a gas body in most situations as humans, because the atmospheric gas body is not enclosed on all sides by a surface that can push back. Because at the edge of space, the space is not pushing back on the atmosphere. The Earth's surface is, but not the edge of space. And so if you think about it, you aren't going to be able to have a uniform pressure, the same pressure throughout the entire gas body, like we saw with the air compressor, if you don't have a case where the entire boundary surface of that body, that gas body, is able to push back, at least to some degree. So why can't you have a uniform pressure if a portion of the boundary of a gas can't push back? Well, actually, you could have a uniform pressure of 0, so pure vacuum. But other than 0, if a gas or liquid body is going to have some pressure greater than 0, that at any given moment is uniform throughout the entire body, why must all boundaries of the body be able to push back? Well, because if a certain boundary can't push back, then there can be no pressure at that boundary, right? And if it was ever the case that for some reason the gas wanted to increase its pressure at that boundary, it's just going to expand past the boundary. And so it isn't the case that the atmosphere as a whole has a uniform pressure throughout. The pressure of the atmosphere increases the closer you are to Earth's surface due to the gravitational weight of atmosphere above. And then at any given location on the surface of the Earth, whether it be sea level or in a mountain city, in that general region, we consider the atmospheric pressure to be effectively the same. So like in a lab or at an industrial plant, we state that the pressure of the atmospheric air around us is some constant value based on whatever the elevation of our latitude and longitude location is relative to sea level. So at some location on Earth's surface, like, here's an industrial plant, right? You're in some city, some latitude and longitude location, you could view the atmospheric air around you as a gas body. This gas body is enclosed by Earth's surface below, and then say 100 feet up from ground level is another surface of the gas body that's enclosed by all atmospheric air that's 100 plus feet above ground level. And that surface can push back. And so in this case, it would be an accurate approximation to say that the entire pressure throughout this entire gas body is uniform. It's a constant value equal to atmospheric pressure. And so that's what it was talking about here. And that if you were to hold a piece of paper tight with both hands above your head, you might expect the paper to bend due to the pressure of air acting on it, but this doesn't happen. What they're saying is that, so if you're holding a piece of paper above your head, right, you're holding it taut, well, you might expect the atmospheric pressure above it to cause it to bend in a little bit, or maybe even bend a good bit. But this doesn't happen because the nature of pressure is that it causes a force on all surfaces that the fluid body is in contact with that corresponds to the pressure. But the orientation doesn't matter at all. So what that means is that wherever the air, the atmosphere is contacting this paper from above and below and even at the thin edge, the gas pressure is causing a force normal to the surface. So you've got forces here, and then even really small forces here because the area is small, but still. You're holding the paper taut in that respect, so you're overcoming those forces. But as far as the forces in the vertical direction, the pressure is just effectively compressing the piece of paper. All objects on Earth's surface are effectively just being compressed by the atmosphere. Okay, but like in general, if you're dealing with any full gas or liquid body that has a large change in elevation across the body, like the atmosphere or the ocean or a lake, then the pressure is not going to be uniform throughout the body because of the influence of weight and gravity. And at a boundary of the body, if there isn't some other solid, liquid, or gas substance to push back, then there can be no pressure at that boundary, like at the edge of space, for example. At the surface of the ocean, though, you do have a boundary, right? The surface of the ocean is not a vacuum like empty space. Atmospheric pressure is pushing down on the surface of the ocean. But as you go to different depths in the ocean, you also have the weight of ocean water pushing down in addition to the atmospheric pressure, so that the pressure changes, the pressure increases. Now, note, it does say here that the actual value of atmospheric pressure depends on location, temperature, and weather conditions. And so, yeah, we know that with storms and whatnot, atmospheric pressure at a given latitude and longitude location can change with time throughout the day, but from day to day, etc. But it's still an accurate approximation to assume that at any given time, whatever the atmospheric pressure is a constant value all around us, like in a lab, at an industrial plant, etc. Okay, so then how do we measure what the atmospheric pressure is around us? How do we measure gas pressure? Well, you can imagine how there are modern gas pressure gauges today that are digital, but it's useful to start by thinking about some of the original methods used to measure atmospheric and gas pressure. So one of, if not the original, devices used to measure atmospheric pressure is the barometer. So it says, how is atmospheric pressure measured? The barometer is probably the most familiar instrument for measuring atmospheric pressure. A simple barometer consists of a long glass tube closed at one end and filled with mercury. If the tube is carefully inverted in a dish of mercury so that no air enters the tube, some mercury will flow out of the tube into the dish, creating a vacuum at the top. The weight of the mercury remaining in the tube is supported by atmospheric pressure acting on the surface of the mercury in the dish. Okay, so a barometer, as far as how it operates, can technically be filled with any liquid. You can have any liquid be the working liquid. It doesn't have to be mercury, but mercury is ideal for a couple of reasons. So first, note how, as we talked about earlier, in reference to the periodic table, mercury is pretty unique in that it's the only metal that is liquid at standard conditions. Okay, so one reason mercury is an ideal liquid to use for a barometer is it's heavy, or it has a high density. Okay, now the second reason is that it has a very low vapor pressure in standard conditions, meaning it evaporates slowly. So we're going to learn in this course how a substance doesn't have to be at its boiling point to evaporate. We're already intuitively familiar with this concept, right? Because like after it rains, we know that water evaporates without boiling. Now, you can stop a substance from naturally evaporating into the atmosphere by enclosing it, right? But with a barometer, you can't do this because the operation of the barometer is dependent on at least some portion of the working liquid interfacing with the atmosphere, because you're measuring the atmospheric pressure. And so that's why the lower vapor pressure of mercury is ideal. Its high density is also ideal, and we'll come back to the specific reason for this in a second. Okay, but the general idea is, and this is a simplified view of how a barometer is built. So you would have a tube and a dish filled with mercury. If you carefully then invert the tube in the dish, carefully in the sense that you make sure that no air enters the tube, then what will happen is a little bit of mercury in the tube is going to flow into the dish. So the surface level of mercury in the dish will increase a little bit, and you're left with, at the top of the tube, this empty space that's going to be a pure vacuum. Vacuum meaning there's nothing at all. There's no gas, nothing at all pushing on this surface here, on this mercury surface. The pressure is zero. Now, but as far as the surface of the mercury in the dish exposed to the atmosphere, well, this surface is being pushed, right, by the atmosphere. There's a pressure on this this surface of the mercury, it's the atmospheric pressure. And so the idea is when the tube is inverted, the mercury is only going to flow out of the tube so much as it can push back the atmosphere here, right? It's going to be based on the weight of the mercury in this column. It's going to be wanting to flow out due to gravity. But in order to flow out, it needs to push atmosphere back. But note that this weight of mercury that wants to flow out has no help whatsoever from some gas pushing here. What's pushing back on the atmosphere is purely the weight of the mercury in this column. That's why it's important that when you invert the tube, that no air gets in. This needs to be a pure vacuum. And so there's going to be an equilibrium established then, in which the atmosphere is effectively holding up a column of mercury at a given height, of the mercury in the tube. Now, you can think about how the tube inverting process, you might say, well, okay, well, doesn't the tube, when you invert the tube, don't we need to make sure that the tube, the open end of the tube stays right at the level of the surface of the mercury? Well, no, not necessarily. You could actually have you could invert, if it's easier, you could invert the tube with the open end dipped well below the surface of the mercury. But all you would have to do in that case is you're going to start the scale where you measure the height of mercury being held up by the atmosphere at the surface of the mercury in the dish. So if this was extended down to here, that's fine, but you wouldn't start the scale, or at least the 0 point on the scale would start here. Because anything below the surface, that wouldn't be included in what's being held up by the atmospheric pressure, right? This height of mercury being held up is relative to the surface of the mercury in the dish. Okay, and so that's why 1 unit of pressure that you'll see is millimeters mercury. That's a unit of pressure. Any pressure that you ever come across, if it's given in pascals or PSI, whatever, that pressure you can convert to the unit of millimeters mercury if you want. Okay, now what about the fact that mercury is heavy or dense? Why is this an ideal property of mercury for a device like this as well, in addition to the vapor pressure? Well, because if you built a barometer out of, say, water, it would still work, at least if you kept refilling it, since the water would evaporate much quicker than mercury, but it would have to be much bigger because water is lighter than mercury, and Earth's atmosphere can push a column of water a lot higher up a tube. So if you used this same setup here with water, and then you inverted the tube of water, no water would flow out, and you'd actually have a pressure here at the top because the atmosphere would be pushing too hard on the water. That you need the tube to be longer to actually get a measurement. You're going to need some empty space here at the top to be sure that you're truly getting a measurement of the weight of the working liquid that's being held up by the atmosphere. Now, but if you think about it, though, if you did build a bigger device that could work with water, a bigger barometer that could work with water, this actually would be beneficial from the standpoint of resolution, in that a smaller change in pressure could be sensed by a barometer with water as the working fluid. But in general, more compact barometers and manometers, which we'll talk about manometers in a second, are more desirable and have enough resolution when built with mercury. Now, you might be thinking that, so this unit of pressure, millimeters mercury, isn't this dependent on the diameter of the tube, right? Because like the amount of mercury that the atmosphere is holding up is not just dependent on the height of the column, but also the diameter. You would take the diameter and do pi d squared divided by 4 to get the cross-sectional area of the tube. Multiply that by the height of mercury. Now you have the volume of mercury. Multiply this by the density of mercury to get the entire weight that the atmosphere is holding up. And with that in mind, couldn't you build a barometer using water as the working fluid with a larger diameter tube? Therefore, for a given height, the atmosphere is needing to hold up a bigger weight of water, right? Or even just adjust the size of the dish with a larger or smaller area of the working liquid exposed to the atmosphere, you can change the total force of the atmosphere that's applied to the liquid. And then also, how is a distance a unit of pressure? Isn't pressure force per unit area? Well, okay, yes, that's true. But first of all, just remember that this millimeters of mercury isn't just a distance, right? It's a distance followed by a substance. Okay, but we'll come back to the exact meaning of the millimeters mercury unit in a second. But first, in regards to building a barometer with different dimensions, the diameter of the tube, or the size of the dish, the diameter of the dish, doesn't matter. No matter what size you make the tube or the dish, for the same atmospheric pressure, which the atmospheric pressure is going to be the same, that's like the constant in the design of the barometer, the atmosphere is going to hold up the exact same height of mercury. So again, I'll say that again. For the same atmospheric pressure, which that is, when you're designing this, that's a constant. You can't adjust the atmospheric pressure. No matter what diameter you would make the dish or diameter you would make the tube, the height of the working liquid, the height of the mercury, is going to be the same no matter what. And so that's why this unit of pressure, this millimeters mercury, is completely sufficient in specifying a pressure. No other information is needed. In fact, you can technically, to specify a pressure, you can give some distance followed by any substance, any liquid substance you want. And really, you could do this for a solid or gas substance as well. It's the same idea, and that would make sense as a pressure. Now, to my knowledge, this is the only, as far as pressure distance, that millimeters mercury is the only standard distance substance pressure unit. But I'm just saying that technically, you can put any distance you want followed by a substance, and that would have the same meaning, the same meaning as a pressure as millimeters mercury. Now, a pressure like this in millimeters mercury is really in reference to, or in the context of, what's called a hydrostatic pressure, which is pressure in a fluid directly related to the force of gravity. Okay, but a hydrostatic pressure still is a pressure just like any other fluid pressure. It's just that it's given its own name to put it into a category of different types of pressure. Okay, like what I mean is the pressure in this air compressor tank, or the pressure of the oil in this oil pipeline. These aren't put into the category of hydrostatic pressure. So yes, the air, the compressed air in this tank is static. It's not moving, but the portion of the pressure in this air, which like the pressure at the bottom of the tank would be experiencing a tiny bit of hydrostatic pressure from the weight of air above it, that's so negligible compared to the 100 psi pressure exerted by the compressor on the air. That's just tiny and negligible. We just state that the entire uniform pressure in the tank is 100 psi, and just ignore the pressure that's coming from gravity. So you don't look at the pressure on this gas as a hydrostatic pressure. It's the same idea for the oil in this pipeline. It goes through a pump, and so it's being pumped through the pipeline. You could say, well, the oil at the bottom of the pipe is being weighed down from the oil at the top, but that's negligible. First of all, that height is tiny anyway, just the diameter of the pipe. But then second of all, when you add in the actual fluid pressure that's supplied by the pump to the oil, you just effectively say there is no hydrostatic pressure. However, when I'm saying that a hydrostatic pressure is a pressure just like any other pressure, what I mean is that you can take the pressure of the oil in this pipeline, let's say it's 800 psi, or the pressure of the air in this compressor, that's like 100 psi, and you can convert that to millimeters mercury. Go to any conversion software, like the Google converter is really nice. You could convert pascals or psi to millimeters mercury, or vice versa. They're both just pressures. This is just another way you can view pressure. It's just another perspective. You would be saying that, look, the oil in this pipeline, the pressure that the oil in this pipeline is under, is equivalent to this height of mercury, the pressure created by whatever this height of mercury is. So let's say, if the oil in this pipeline was 800 psi, then in millimeters mercury, that's 41,372 millimeters mercury. So the oil in this pipeline, the pressure on the oil in this pipeline is equivalent to a column of mercury that's 41,372 millimeters high. That's it. It's just another perspective. Okay, but still, how does this work? Why don't the dimensions of the tube or the dish matter as far as the resulting height of the mercury at a given atmospheric pressure? Well, this is because pressure is normalized with respect to area. And so because of this, the area of the working liquid exposed to the atmosphere or the cross-sectional area of the tube don't matter. No matter what size you make the dish, the pressure on the surface of the mercury from the atmosphere is going to be atmospheric pressure. And as you go through the working liquid to the base of the tube, all the way to the top of the tube, at the top of the column, you go from atmospheric pressure all the way down to zero pressure, vacuum. This is always going to be the case 100% of the time, no matter what dimensions you make the tube or the dish. No matter what, the pressure at the zero tick mark on the tube is going to be atmospheric pressure, no matter what dimensions you use. Okay, so if you made the tube diameter smaller, what does that mean? Well, okay, less liquid needs to be held up. So can the atmosphere push the column higher? Well, no, because the cross-sectional area at the base is smaller. If you made the tube diameter larger, well, does that mean that for the same atmospheric pressure, the larger weight of liquid is going to cause the height in the tube to drop? Well, no, because there's a larger area at the base of the tube, which is more, in terms of pressure force per unit area, that's more force. Okay, and so that's why, from the perspective of hydrostatic pressure, the formula for hydrostatic pressure is just, so the pressure is equal to, you have height times the density of the working liquid times the gravitational constant. As far as the dimensions of a given system, the only constraint is height in this formula, the height of the column. The density is fixed by whatever the working liquid is, and the gravitational constant is the same anywhere on Earth, which is the only place we would be designing the barometer, right? Okay, so what you've got is in SI units, so height is a meter, then density is kilograms per cubic meter, and then the gravitational constant, that's an acceleration. So you're left with kilograms per second squared meter, which is pressure. Remember, this is really just newtons per square meter. This is just simplified all the way down to pure base units. Okay, and so you can see now how the units for pressure of a distance times a substance correspond to actual units of pressure in terms of force per unit area. When specifying pressure as a distance times a substance, you're mainly referencing this hydrostatic pressure formula on Earth. So the density corresponds to the density of the substance specified. The height corresponds to that's the distance. So you have the unit is distance, and then there's the substance, and then the gravitational constant, you're always on Earth. And so that's how you get what pressure that unit is referring to in actual pressure units of force per unit area. Now, again, I say that you're mainly referencing this hydrostatic pressure formula when specifying a unit like millimeters mercury. You're only mainly referencing this formula. It's not like a unit like this is restricted to this formula, because it all comes down to, it's a pressure just like any pressure. It's a force per unit area. So you could calculate the pressure of a fluid coming out of a pump or compressor and say pascals or psi with another formula, and then convert that to millimeters mercury if you wanted. So, okay, it says standard atmospheric pressure, 1 atm, is equal to the pressure that supports a column of mercury exactly 760 millimeters or 76 centimeters high at 0 degrees Celsius at sea level. In other words, the standard atmosphere equals a pressure of 760 millimeters mercury, where millimeters mercury represents the pressure exerted by a column of mercury 1 millimeter high. The millimeter mercury unit is also called the torr, after the Italian scientist Evangelista Torricelli, who invented the barometer. Okay, so this I always personally found a little bit confusing at first, because earlier in the video we talked about how when discussing properties of elements in the periodic table, or even just general substances, not strictly elemental forms, unless stated otherwise, it's implied that the discussion is in reference to the substance being in a surrounding environment that the textbook called normal. So these normal atmospheric conditions of 25 degrees Celsius and in 1 atmosphere pressure. So, okay, most of the time, atmospheric and like environmental conditions are going to be the same thing, right? Like, I guess the environment in reference to an aqueous solution wouldn't correspond to atmospheric, like in reference to Earth's atmosphere. But still, if you had a reaction in aqueous solution taking place in a lab or at an industrial plant, you can still think about what are the overarching environmental atmospheric conditions in terms of temperature and pressure. Maybe in thinking about a system that's inside the human body, the environment and atmospheric conditions are pretty separate. But even in that case, they aren't completely separate because the atmospheric pressure does have an effect on our bodies, right? So, but okay, when having general discussion about elements in the periodic table or just any substance in general, unless stated otherwise, it's implied that the discussion is in reference to the substance being in a surrounding environment that the textbook calls normal. Normal meaning 25 degrees Celsius, so around room temperature, and an atmospheric pressure of 1 atmosphere. But if we come back to the definition of atmospheric pressure, not the definition of atmospheric pressure, the definition of the unit of pressure called the atmosphere. So standard atmospheric pressure, 1 atmosphere, is defined relative to a temperature of 0 degrees Celsius. Okay, so first of all, as I mentioned earlier, it's important to note how the textbook didn't make any official statements here about how we're focusing on in this chapter the behavior of substances that exist as gases at quote-unquote normal atmospheric conditions of 25 degrees Celsius and 1 atmosphere. Nothing is bolded or italicized anywhere here, right? And also the word standard isn't ever used. But here, with the definition of standard atmospheric pressure, this is bolded, right? This is like an official definition, an official statement here, and also the word standard is used. So, okay, the way this works is the terms standard temperature and pressure, or STP. You're going to hear this a lot. Well, there's not one universal standard temperature and pressure that everyone in all scenarios references. So again, just to make this clear, just to make sure we're clear on exactly what we're talking about here. So the vast majority of systems we work with in any scenario in science, engineering, physics, etc., any real life physical scenarios in physical science are going to be taking place in some context on Earth, right? Not in all scenarios. With physics, you could go into outer space and whatnot, but the vast majority of all science, engineering, physics problems that we work with, the system is somewhere on Earth. So the question then is, what do we call the standard conditions of the general environment around us, or the standard conditions of the atmosphere? You know, and again, even if you have a system like inside the human body, where like the standard temperature there is what, like 98 degrees Fahrenheit and whatnot, but it's still in any physical science, real life scenario, you're still going to want to have as a back thought, you know, what's the surrounding environment of Earth? What's the standard environment, temperature and pressure? What's the reference point for the environmental conditions around us, Earth's environment? Okay, well, you can specify the conditions of the atmosphere, of Earth's atmosphere, with a temperature and a pressure. And so like the textbook called 25 degrees Celsius and 1 atmosphere normal, but like in engineering, normal temperature and pressure, or NTP, is 20 degrees Celsius and 1 atmosphere. So that's still, I would say, a little bit below room temperature. 20 degrees Celsius is 68 Fahrenheit, but that's what NTP is. And sometimes you'll see the reference conditions of 0 degrees Celsius and 1 atmosphere. I'm going to go through the details of the different reference environmental conditions and why they're used in another video, but most likely in the units and measurement playlist. But if you noticed, all the environmental conditions I just stated had a reference environmental pressure of 1 atmosphere, right? And so the different STP references are going to differ in regards to the temperature. But the reference point for the environmental pressure is pretty universally agreed upon to be 1 atmosphere, with the term atmosphere referring to a unit of pressure defined, so relative to sea level. Everyone agrees that the reference environmental pressure should be, or atmospheric pressure, Earth's atmospheric pressure be relative to sea level. I should be saying atmospheric, not environmental, because the environment is just system specific, right? The environment inside of a pressure vessel at an industrial plant is going to have a different pressure than outside in Earth's environment. But for the general atmospheric environment on Earth, the standard reference pressure that everyone agrees upon, to where it even gets defined in its own specific unit of pressure called the atmosphere, is based on the environmental atmospheric pressure at sea level. But even more than that, when the temperature outside is 0 degrees Celsius. And you could think about also, it wouldn't be like a stormy day. It would be a dormant, non-cloudy day. So you can imagine back in the day, maybe scientists put a bunch of barometers at different sea level locations. And the first barometer that was exposed to a steady temperature outside of 0 degrees Celsius on like a dormant, non-stormy day, the height of the mercury column in that barometer was recorded to be this 76 centimeters, 760 millimeters of the height of mercury. And a new unit of pressure called the atmosphere, or the ATM, was defined to where 1 atmosphere was equal to this pressure of 760 millimeters mercury. That's why it says exactly here, because this is the definition. This is the definition of the atmosphere. Okay, now, why was this done at 0 degrees Celsius? Why not something more around room temperature? Well, that's a discussion for another video. Okay, now, you also might ask yourself, if we come back, so it says normal atmospheric conditions in this context are 25 degrees Celsius in 1 atmosphere. So does this imply that this is the atmospheric pressure at sea level at 25 degrees Celsius? No, not at all. This is the unit of atmosphere, the ATM, 1 atmosphere. An atmosphere is defined in reference to this definition right here. So anytime you see, no matter what the context is, the pressure unit of atmospheres, it's always in reference to this definition. Always. Okay, now, next, it also talks about the unit torr, to where 1 torr is equal to 1 millimeter mercury. A torr and a millimeter mercury are the same unit. They mean the same thing. And so all the torr it's just an alternative way you can express. You can use torr instead of millimeters mercury if you want, and sometimes it is used. And it's just a name, an alternate name given in honor of the scientist who invented the barometer, this Torricelli. Okay, now, a manometer is a device used to measure the pressure of gases other than the atmosphere. So, okay, once again, you can imagine how there's more advanced modern pressure gauges, pressure transducers, digital pressure transducers that can measure atmospheric pressure, or pressures like inside what they're referring to here, like a pressure inside of a vessel, not the atmospheric pressure, some other pressure. Okay, but it's still useful to, when learning about the meaning of pressure, the fundamentals of pressure, it's useful to think about the original pressure measurement instruments and how they worked. So again, you had a barometer was one of the original devices, if not the original instrument used to measure atmospheric gas pressure. And now they're talking about the manometer, which is a device that measures the pressure of a gas other than the atmosphere, like a gas pressure in a container. So the principle of operation of a manometer is similar to that of a barometer. There are 2 types of manometers. The closed tube manometer is normally used to measure pressures below atmospheric pressure, whereas the open tube manometer is better suited for measuring pressures equal to or greater than atmospheric pressure. Nearly all barometers and many manometers use mercury as the working fluid, despite the fact that it is a toxic substance with a harmful vapor. The reason is that mercury has a very high density compared with most other liquids. Because the height of the liquid in a column is inversely proportional to the liquid's density, this property enables the construction of manageably small barometers and manometers. Okay. So here they show a closed tube manometer, and here's an open tube manometer. What that's referring to is this end of the tube here. So this is here it's closed, and here it's open. And you've got the gas in the container here that the manometer is measuring the pressure of. And the idea is, like we talked about, with a pressure in a container or a vessel, in most circumstances, at any given moment, we're thinking about the pressure being a uniform value over the entire gas volume. In these scenarios, hydrostatic pressures are negligible. The pressure here at the bottom of the container due to the gas above is completely negligible. The weight of the gas above is negligible. We're just looking at this as there's one uniform pressure throughout this entire gas, and that's what the manometer reading is going to give us. Okay, so let's see. This gas pressure is being contained by, you have a valve here, you've got the surface of mercury here, and then just obviously the walls of the container. So that this valve, you can think about how you could open the valve and release the gas, or you have the valve open and you can pump the gas in. Okay, so with the closed tube manometer, in general, your goal is to measure the pressure of a gas that's below atmospheric pressure. And so with this then, with the closed tube, the idea is this empty space here is a vacuum. You have nothing pushing back on the mercury. The pressure here is zero. So the entire pressure of this gas is going to go to just strictly pushing this column of mercury up. If the pressure of the gas was zero, then, or if there was no gas here, then the mercury would be in equilibrium to where the surface on the left here and on the right, the two surfaces of the mercury would line up. But when you have a gas pressure, the gas pushes down on the mercury here and it pushes up here, and when it comes back to equilibrium, you have the gas pressure holding up a certain height h of mercury. And that height h is, because there's no pushback here at all, this is vacuum, that height h is the pressure of the gas. And this is called the pressure of the gas is equal to this P sub h. Just read off the height of mercury. That's called the gauge pressure, because you just read it straight off the gauge, the manometer gauge. So again, for an open tube manometer, the pressure of the gas, the actual pressure of the gas, is equal to the gauge pressure. You just read it straight off the gauge because there's nothing pushing back here. Now, you can think about how it's not like you couldn't potentially measure the pressure of a gas that's under a pressure that's above atmospheric pressure with a closed tube manometer. The only requirement is you just need to make this end of the tube however long you need to make it, right? But in general, the idea is you're going to use a closed tube manometer to measure the pressure of a gas that's below atmospheric pressure. If the pressure of the gas is above atmospheric pressure, then in general, you're going to use the open tube manometer, to where this end of the tube is open and you've got atmospheric pressure pushing down on this end. And so here, the gauge pressure, which you read straight off the gauge, this height of mercury, is not the actual pressure on the gas, right? The actual pressure on the gas is the gauge pressure plus atmospheric pressure. So you would add, in terms of millimeters mercury, you would add P sub h, then add 760 millimeters mercury to get the actual pressure on the gas. Now you can think about how in this case with the open tube manometer, if the pressure of the gas was below atmospheric pressure, then you actually couldn't measure that pressure with an open tube manometer, because the gas isn't going to push the mercury column up at all. P sub h is going to be equal to zero. So the only information that would give you is that the gas pressure is something below atmospheric, but you don't know what.